So this is the session in which, as you know, we are doing a webinar series in which we have been covering all the building blocks of the cloud. And in this particular webinar, we are specifically doing the software defined storage, which is the fifth in the series. And there are going to be five more coming after this. And we have the speakers lined up for all five of the remaining sessions as well. So all of them are going to be interesting as well as this would be. So with that, I think let's go ahead. Anjana, you can share your screen and we can get going.
Okay, all right. Okay, so good evening, everyone. I'm Anjana Jimmington, currently doing my PhD in the field of network security, focusing on software-defined networking. And yeah, I'd like to thank Nipendra for giving me this opportunity. I hope this
Most welcome.
webinar will give you, and the session will give you a clear insight in what is SDN. So I welcome you all to the webinar. So yeah, so let me share my screen. I hope my screen is visible.
Yes, it is.
Okay.
Yes.
Yeah, all right. So the word SDN, or let's say software-defined networking, this has been in the networking industry for the past 10 years. So all of us, we have been hearing about SDN. Sometimes we hear SDN networks. Sometimes we hear the changing or the translation of a traditional network into a software-defined one. Sometimes we hear about software-defined switches. So we are all familiar with this term SDN. But what SDN actually is, or why do we need SDN? All these, though we know vaguely about all these things, they are yet to be clear into our mind, right? We don't really have a clear picture about like why do we need something called a software defined networking or what actually it is. So I hope this webinar will help you gain a clear insight into why do we need something called as software defined networking, what actually is SDN, and what does SDN do. So this is the
Yeah. So
agenda of
before
the
we,
webinar.
yeah,
Yeah.
I just
Yes,
want to
Nitin.
quickly want to know about what we're doing in your research, right? Can you just elaborate more on that? I know that you just mentioned that you're doing a PhD, but I think we would like to know
Oh,
more about your PhD and what you're doing there. So would be helpful if you can
okay.
talk more about it a bit.
Okay. All right. So, as I've already mentioned, I'm working in network security and focusing on software defined networks. So, basically, my research is focusing on enhancing the security of a software defined network. So, we have basically been working on automating the defenses in SDN, various defenses in SDN, and we're working on that. We're working on enhancing the security of SDN, and we're looking forward of using this enhanced secure version of SDN and like having its applicability in various fields such as IoT, clouds, etc. So that's why my area of focus is in research. We have students here. We have MTech and MSc students who are also working on SDN, and yeah, we have a practical test bed also where we test in the algorithms and the solutions that we develop here. So that's about my research in SDN.
Okay, great. Good to know about that. Yeah, we can move forward. Yeah.
All right, so this is the agenda of the webinar where we will see why and what is SDN, the benefits, the architecture, the controllers, the open flow, the flow tables, the working, and finally we have the SDN and the cloud computing with containers and Kubernetes, the case studies and challenges. So yeah, so moving on to why and what is SDN. So first, let's see why do we need something called as SDN. So let me talk about the history of internet. If I'm talking about the history of internet, the history of internet dates back to the 1980s, where the US introduced the concept of the ARPANET. ARPANET is Advanced Research Project Agency. So this ARPANET was the first introduction in internet introduced by the US in 1980s. So what happened was in the journey ahead, they adopted the TCP protocol, or let's say the transmission control protocol. So with the adoption of this TCP or the transmission control protocol, they made this ARPANET publicly available. This was made publicly available to the users, and they changed the ARPANET into the NSFNet, that is National Science Foundation Network, or the NSFNet. After that came a significant change to the internet architecture, which made it more popular among the community. And that was for the introduction of the WWW, or the World Wide Web, and the OSI protocol, or let's say the OSI model. Now, after the OSI model was introduced to the community, there had been a lot of small changes happening in the architectures and things like that, but there has not been any fundamental change happening to the network architecture. So, OSI model was considered to be the fundamental architecture of the network, and after that, no other change had happened. Now, what happened was, as years passed by, the internet became more popular, and like people started using internet for various things, and their domain started expanding so much. The current OSI architecture started facing a lot of challenges. Say, for example, quality of service, scalability, security, privacy, and even network management. And also, along with this, with the invent of the Internet of Things, let's say the IoT, what happened? There started becoming an incorporation of various heterogeneous devices and their services. All this made the network management a very big concern for the network administrators. They found it really difficult to manage the network, and these started giving rise to a dramatic increase in the security attacks, posing severe challenges. Now, here comes the need of something called as a software defined networking, or SDN. So, SDN marks the first fundamental change in the network architecture after the OSI model. So, SDN here has become an important paradigm for the future networking architecture. Potentially, they have the ability to overcome some of the barriers of the legacy network architecture. For example, say the legacy network architecture, they follow the protocols in the TCP IP stack. But SDN, they give you a totally flexible and programmable platform for their functioning. And that is what makes it like very reliable and very flexible for the network administrators to to meet almost all the challenges that the traditional or the conventional OSI model, OSI architecture were possessing. So that is why we needed SDN. So SDN basically was introduced to conquer or to solve as a solution to a lot of challenges that the OSI model had to face as the network started expanding. So that is about why we need SDN. And before moving into what is SDN, we all know what is the OSI model, right? So let's take a look at this OSI model. We're all familiar with this. This is the OSI model, and this is a 7-layer model. As you can see, starting from the physical layer up to the application layer, we have the 7 different layers which help to the complete data transfer from a client to a server, or let's say from a sender to a receiver. So here, as you can see, the physical layer, the data link layer, and the network layer. These 3 layers are exclusively used for network management in a traditional network. And these 3 layers, they have the network devices in them, such as switch, hubs, routers, etc. And they have the intelligence of taking decisions and the intelligence of forwarding the packet. So this is the normal or the traditional or the conventional network architecture that we're talking about, the 7-layer OSI model. And this was the first fundamental network architecture. So before we move to the SDN, let's see how was a traditional switch looks like. So basically, this
Anjana,
is how.
Anjana, just a minute, Anjana. I think some of the
Yeah.
folks are having the issue with the webinar. I know that one person has mentioned on the chat. Our others are also facing the same issue. Are you not able to watch the video?
Okay.
Can anybody else confirm, or is just issue with one of the person? No. Okay, we can. No, it's fine. Okay, so I think Sajid, just check maybe at your end if your network speed is good. Seems to be fine, and we'll anyway have a recording of the session, so don't worry about that. But I think it seems to be okay. Yeah. So okay, so I think we are okay. So, but it's a bit lagging. Some comments are there. Okay, I don't know. So Anjana, maybe you can also stop your video for time being, and then that will be good for others. Is that okay?
Sure, sure. Yeah,
Yeah,
sure.
thank you. Yeah, we can
Okay,
go
so
ahead,
yeah, so
Anjana. It's
that's
just that videos.
okay, okay, sure. Okay, sure. Yeah, so that's about this OSI model, or let's say the traditional network architecture. So now next, let's see how a traditional switch looks like. So this is a traditional switch, and as you can see, the traditional switch has a data plane and a control plane. So the traditional switch architecture comes with an inbuilt data plane and a control plane. Now, the data plane, it follows the instructions given by the control plane and forwards the packet accordingly. So for example, here you see we have port 1. Now this port 1 wants to send a data packet to port 2. So what basically happens is port 1 sends it to the data plane. The data plane forwards this packet for decision making to the control plane residing within the same switch. The control plane analyzes the packet, it does the analysis, and it finds the routing protocols, the MAC address mapping, whichever forwarding table it belongs to, and then it takes a forward decision. Once the decision is taken, here the decision is to forward the packet. The decision is forwarded to the data plane, and the data plane sends the packet to the port 2. So this is how a traditional switch works, and this is a traditional network switch architecture. So as you can see in a traditional network architecture, say this is a switch, every switch has its own intelligence, which is the control layer and the forwarding layer. So the decision making and the intelligence both belongs to the specific switch itself. Or here we can say in a traditional network, the intelligence and the decision making capability is distributed. It is distributed to every single switch in the network. So that is the main thing that you should keep in mind regarding a traditional switch or a traditional network architecture. Whenever you are sending a packet from one port to another port, every switch in between has its own ability or its own capability of analyzing the packet and taking the decision. That intelligence is exclusively there for every single switch, and that is decentralized. Now, differentiating from this, the SDN is a paradigm that separates the control plane from the data plane. As you can see here in the traditional network, we have the control plane and the data plane residing on one switch. Whereas when we are moving on to a software defined network or the SDN, they are separated. A master device called the controller is in charge of the control plane, and the switches, they just act as the dummy forwarding devices. So that is the main difference between a traditional network and a software defined network. Traditional networks make sure that every switch has its own control plane and data plane, whereas software defined network makes sure that a centralized master device called as the controller is in charge of the control plane, and we have programmable switches. Now the control plane, it is the decision maker here. The controller decides how the traffic should be routed, and the data plane is responsible for forwarding the packets according to the decisions made by the controller. So this is basically what is SDN. So basically in one line we can say what is SDN means. SDN is a paradigm that separates the control plane from the data plane. So now we will take a look at the architecture of a software defined network. So as I already mentioned, after the OSI architecture, another fundamental architecture that came into place and that was accepted as a standard is the software defined network architecture. So basically in networking, we have two architectures. One is the OSI 7-layer architecture and the SDN's 3-layer architecture. Now the 3-layer architecture of SDN, we have the data plane, the control plane, and the management, or we also call it to be as the application plane. Now the management plane or the application plane, they are responsible for managing the entire networks, or let's say the applications run on this application plane. Now we have coming down, we have this control plane, and this control plane is responsible for controlling the data plane. And let's say the controller resides in this control plane. We have SDN controllers residing here, who are the intelligence and the decision makers of the network. Coming down, we have the data plane, and it is responsible for forwarding traffic through the network. So the decision comes from the control plane, and the data plane devices or the switches here, they just obey those rules, or they just work accordingly to the suggestions given by the control plane. Now, how they communicate? How is this communication happening between the data plane, the control plane, and the management plane? That is with the help of this interfaces. So as you can see, in between the data plane and the control plane, we have this southbound interface. Now, southbound interface helps in the communication between the data plane and the control plane. And an example for the southbound interface is the OpenFlow protocol, which we'll be looking into detail later. So this protocol helps in the communication, helps in the perfect communication between the control plane and the data plane. Now for the communication between the control plane and the management plane, we have the northbound interfaces. Now northbound interfaces, they are just the normal REST APIs that we see. Now if you are using more than one controller, then the communication between them. For that, we use the east or the westbound interfaces. So that's about the architecture of a software-defined network. Now moving on to the controllers, we have these are some of the controllers that are widely used. Of them, Knox, Ryu, Onos, Floodlight, Open Daylight, all these are widely used by researchers and industry professionals. Whereas Mastero and Noteflow, they are not widely used, but all these controllers, they come with inbuilt functionalities, and each stay distinct from every other controller with their ability to manage the network in a good way. So these are some of the very commonly used SDN controllers. Yeah, so that's about the SDN architecture, and the SDN controller. Now we have OpenFlow. So I've already mentioned the term OpenFlow. I've already told that OpenFlow is a protocol that facilitates the communication between the the control plane and the data plane. It is an example for the southbound interface. So OpenFlow, it is a protocol that enables centralized control of network switches and routers, allowing for programmability and dynamic management of network traffic flows. So this is a fundamental concept of the SDN. So using OpenFlow, the network administrators can define and manage traffic flows, specify how to forward the packets, and apply policies to the network device through a centralized controller. So that is basically what is OpenFlow. It's basically a protocol that enables a centralized control of network switches and routers, allowing programmability and dynamic management of network. Now, since it's a protocol, you can write it in any language of your choice. Say you can write in Python, Java, C++, Golang, etc. So you can write it in any language, in the language in which you're choosing your controller, because you should be able to communicate with the controller, and all controllers work on different programming languages. So based on the choice of the controller, you should write your OpenFlow. So that's about the OpenFlow. And yeah, so we've covered SDN, the architecture of SDN, the controllers, and finally the OpenFlow. Now, another very important concept that we have in SDN is the flow table. So yeah, we are all familiar with routing. Yes.
Anjana, I have one question just to I have one question actually. So maybe others maybe have a similar question. Would it be possible for you to go to that the diagram of control flow, management flow, and data controller, what you have there, right? A couple of few slides back. Can you just go back? Yeah, here. So the
Um,
data plane, what we have. So data plane are they going to be your switches, or they're going to be regular devices? What we have, like regular
uh,
systems, VMs or something like that. What we are going to have there.
no, data plane will be the forwarding devices.
Okay, so
It
these
would be
are
the
your.
switches.
Come again.
It would be the switches.
Switches. Okay, okay, okay. Got it. Got it.
Okay. Okay. So yeah, I was talking about this flow table. So yeah, the flow table is something very similar to the routing tables that we have in traditional network. So just like that, we have this flow table, and every single entry in the flow table, we call it as a flow rule. Every single entry that we given to the table is called as a flow rule. Now, the flow table typically includes four things: match field, actions, priority, and idle timeout. So the first is the match field. So as the name tells us, match field is nothing but a matching criteria which matches the incoming packets to the flow entry. When a packet comes in, to check if it is a genuine packet, we match it to the flow entry. So this is actually a 12 field entry. This match field has 12 fields to be cross-checked. Say, for example, these 12 things include input, the source MAC, the destination MAC, the Ethernet type, the VLAN ID, the IP port, the IP source, IP destination, the TCP source port, TCP destination, MPLS label, etc. So like this, we have 12, say it's a 12 entries we have. The match field will be having a 12 entry. Just like, what do we say? Just like we have a packet frame in the traditional networks. Now, the matching can happen in four ways. Either it can be a IP matching, or it can have a subnet matching, or it can be a MAC matching, or maybe a TCP or a UDP matching. Okay, so that is how the match field works. The match field is basically used to compare against an arriving packet. When a packet is arriving, we compare it, and four kinds of matching can be done: the IP, subnet, MAC, and TCP UDP. And we have, it is a 12 field, let's say a 12 entry, or we have a frame of 12 things in it. Then the second one is the actions. So actions basically specify what should be done with the packet that has come. So we can take actions to the packet that has arrived. We can either the packet, or we can forward it just like that, or we can modify it. So basically, actions is just that: what should be done with the packet that has arrived. So yeah, that is about the match field and the actions. Then we have the priority. Now, what priority basically is, flow entries are assigned as priority. So let's say a flow table has a lot of flow entries. Which flow entry to take? That is a very big question to be addressed. Which flow entry is to be taken? So there we have priority, and priority plays a very important role there. Whichever flow rule has a higher priority, that will be taken, or that will be chosen. So priority determines which flow entry among the flow table is to be considered. Then we have the idle timeout, or we simply call it as timeout also. That is just a timestamp, or let's say a particular period of time which is kept for the flow to remain in the flow table. Once that timestamp is reached, the entry is removed from the flow table. So these are the four important, or let's say the four sections that we have in a flow table. And a flow table entry, which I already mentioned as a flow rule, is like this. As you can see here, we have the matching rules, and this is the 12 match fields to be considered. Then we have the statistics, which have the packet here, and this is the instruction. It's same as the actions to be taken to the packet that has arrived. And this is basically an example of the flow table. As you can see, every flow table has a number of entries in it. So a priority will be assigned to these, based on which the flow rule can be chosen. So yeah, so that's about the flow table, and flow table is similar to that of the what do I say? It's similar to that of the routing tables that we have seen in the normal networks. So now here, let us see how this SDN or how a software defined network actually works. Okay, so I have a sender here, I have a receiver here. Now this sender is going to send data to the receiver. So here we are going to consider let's say two instances. The first instance is when there is no match with the float table. Okay, that's the first instance. And the second instance is where there is a match with the float table. So we are going to see with these two instances. So the sender is sending a data. The data reaches the first forwarding device. Now the forwarding device checks the float table and it finds out that there is no match. When it finds out, it encapsulates this data and it forwards this data to the controller. The controller decapsulates it and checks, set the rule for it, and sends it back to the switch. Here, the switch looks into the action part and forwards it to the next switch. This switch also looks into the action part, forwards it, and the final switch forwards it to the receiver. So this is how a data is transferred from a sender to the receiver when there is no match with the float table. Now the second case is when there is a match with the float table. So the sender sends data to the switch. The switch checks with the flow table. It identifies the flow rule. It forwards the packet directly to the switch. And from there, it's gone to the receiver. So this is how the SDN works. The decision making or the, let's say the decision making or the formation of the rule that happens at the controller. So when there is no match found, what happens? The controller sets the rule and sends it to the switch. The switch just reads the rule sent by the controller and follows the action or follows a decision, whatever is taken by the controller. The switch does not possess the capability of taking decisions on its own. So this is how a data is transferred in a typical SDN network. We've seen two instances. The first instance when there is no match with the float table, and the second instance when there is a match with the float table. So that's about the working of an SDN network. So from all this, we can of course arrive at a lot of benefits that SDN is possessing over traditional networks. The first thing, of course, is centralized network control, right? Because as we already seen that the traditional network is decentralized. Every switch is controlling it the way it wants to. But here we have a centralized controller who is controlling the network. So centralized network control is a benefit. Then we have improved network flexibility and agility. We have efficient resource utilization, network virtualization we have. It's open standards and interoperability. And of course, it has simplified network management and automation. So these are just some of the benefits of SDN. Now moving on to SDN and cloud computing. So moving on to that, let's see how we can deploy SDN and cloud computing. Let's take a scenario where we like the deployment of SDN in cloud computing will favor there. So let's take a case study here. So, all right, so let me say that there is a multinational cloud service provider. Let me name it something called Cloud Tech or something. So it's a multinational cloud service provider. And this particular firm, they are facing a challenge in efficiently managing its cloud infrastructure to meet up the diverse needs of the customers. So there is a firm, there's an MNC, is facing a challenge in efficiently managing its cloud infrastructure to meet up the diverse needs of its customers. So these are the 4 challenges that this particular MNC is facing. That is resource efficiency, network performance, network isolation, and scalability. So they are facing these 4 challenges. So they have to find a resolution for all these challenges. And for that, they are integrating SDN into their cloud computing environment. So now let's see how the integration of SDN into the cloud computing environment will help them address these four challenges. So first challenge is resource efficiency. So how will SDN help in resolving resource efficiency? Right. So SDN helps in dynamic resource allocation. Let's say SDN controllers, they monitor real-time resource utilization and traffic patterns, and they dynamically allocate the CPU, the memory, and storages. So that's how SDN helps in resource allocation. The second one was network performance. So, how will SDN help in network performance? Yes, SDN will help in optimizing network paths. It will help in choosing the shortest path because it has a controller that has a clear picture, that has an eagle's eye view of what's happening under it. It knows the network, it knows what are the different underlying forwarding devices, the distances, everything. So it optimizes the network paths, it reduces the latency, and it ensures high throughput for data transfers. So that is how the network performance is optimized using SDN. Then we have the network isolation and segmentation. So network isolation segmentation, it's happening in the traditional network also, but it is a bit more easier in case of the SDN, as we just have to tweak out the flow rules, and we can do it, and thereby the isolation can be achieved. So this is how we do it in SDN. Then we have the scalability and elasticity. So the SDN based architectures that help you to scale the network infrastructure dynamically, because you don't if it's a traditional network, if an additional device or additional host is to be added, we have to go programmatically change every single switch that host is connected to. But in the case of SDN, we just have to intimate the controller, just have to let the controller know that a new device is being added. So using this, the scalability is not an issue. However, dynamically the demand spikes, we can add or we can remove devices. And it also seamlessly the migration of VMs across physical hosts to balance load balancing, and all the resource utilization, everything that is a bit more easier when compared to the traditional networks. So with this case study, we can see that SDN, it can be incorporated into any domain, provided we know how to use it and where to use it. So here, this form will be able to address its four concerns of resource management, network isolation, scalability, and network performance by incorporating SDN at the right positions. So this is how SDN can be deployed in a cloud environment. Now, just as we say, every coin has both the sides, SDN also comes up with its own challenges. So, one is the placement of the controller. Where to place the controller? It's a really crucial decision to be taken, because the controller is the core of the network. Then we have single point failure here. That is, if the controller is dead, then the entire network is dead, because we don't have any other intelligence to support the network. That's the second thing. Then let's say interoperability, reliability, all these things gets affected with the failure of the controller. So these are some of the challenges that SDN possesses by itself. But when compared to the advantages that SDN provides over the traditional network, I think these challenges are negligible. Yeah, so that's about SDN. Over to you, Nipendra.
Yeah, thank you, Anjana. That was really informative. So we'll take few questions what are coming on the chat, and I also have one question which I'll ask maybe just after the questions which are on the chat there. The one question was there. I think it is about the slide which you have shared about again the OpenFlow, ONOS, and so on, right? So those are these are all softwares, correct?
Yeah, they are softwares.
Okay. Second question with respect to the diagram which we were mentioning earlier. is it about the data plane components, right? So the data plane we
Yeah.
mentioned about those switches. Now these switches
Yeah.
are hardware devices, or they can be like the normal VMs which we can configure as NFV.
Yeah, you can do that also. Switches are both like they are both. They are hardware as well as virtual switches also. For SDN, we
Okay, so can
have
you give?
its own simulation platform called as Mininet. Just like the packet trace of Cisco, we have Mininet. So Mininet helps you to have your own virtualized switches and your own controller and things. It's a virtualized platform where you can create your own SDN network.
Okay, can you please go to the slide, the same slide which you were mentioning earlier?
Which one?
The controller, different controls you mentioned there, right? The diagram which we have, management control and the data plane and all that stuff, right? Yeah. There are a few questions
This
coming
one.
there. No, not this one, the other one, where we have all three
This
layers.
one. Okay.
Yeah, the next one, I think, after this.
This one.
Yeah, this one. Yeah. So I think the question here is what we're discussing. Go back to the previous slide, please. Yeah.
Hmm.
No, no. Yeah, this one. Correct. Yeah. So here in the data plane, right? So I think what Anjana is mentioning is the data plane component with the switches here, right? These can
Hmm.
be the regular switches what we have. That is correct. And the second part, which we should cover here is NFV, right? So would you mind sharing
Yeah.
a bit about NFV?
Okay. All right. So talking about NFV, it is like virtualizing this. So as I already said, SDN provides the user flexibility and the programmability ability. That is what SDN basically provides the user with. So here, this SDN network, we can see it as two phases. It can be a typical hardware network where the switches are the normal hardware switches we have. And also on the other hand, they can be the virtual switches also. So NFA is basically virtualizing the entire network. And for the purpose of virtualizing this, as I already mentioned, we have simulators like Cisco's Packet Tracer. For SDN, we have a simulator called as Mininet. And this Mininet comes in with the switches, hosts, the controller, everything. So it is a virtual platform that helps you to virtualize it and helps you to create your own virtual network.
Okay, so there's one more point, Anjana. Just want to make sure that it is clear that so now we hear that all of these different providers of the network devices like Cisco, Juniper, and so on, right? They are
Mm.
coming up with their NFV machines. So what I know that is like for example, if I have to implement a given switch, I can implement them in a software. So rather than buying a typical hardware switch, I can actually just get a VM, and in that VM we can have the respective um, virtualized switch in a way, right? So rather than buying switches, the physical devices, I can just get those VMs, and those VMs can
Yeah,
work for me in the data plane. Correct?
yeah,
Okay, okay. Yeah, that is how I think NFV is. So NFV is the device which are VM devices, or which can so we can virtualize load balancer, we can virtualize switches, router, and so on. And I think they can switch, they
yeah,
can come in place of data planes, and our SDN can program all the routes and then control those VMs so that the traffic goes in and out from them. Yeah.
yeah,
There's one question
exactly.
also on the chat is SDN controller can be written in different languages and they are software. So
Yeah, they
are
are
they do
software.
are they correct? So they are software. Yes,
They
correct.
are software.
Roughly that is a software. Yes.
Yeah, it's a
Any other questions, guys? Any other questions? Okay. So with that, I can take over. I can share my screen now, Anjana. You can unshare yours. I can start
okay.
sharing my screen. Yeah. Yeah. Let me share my screen. Um, so Okay, great. Hopefully you can all see my screen. Just want to give a quick intro about myself, and then we'll kind of jump into the slide which I have. So my name is Nipendra, and I'm founder of Cloud Yuga, and we have been training corporates and individuals on container technologies for close to 8 years now. I authored a book on Docker in 2015, seems ages now, and also published a couple of courses for the CNCF, and including the first Kubernetes intro course for the CNCF taken by more than 200,000 learners across the globe. And I also organized the Kubernetes Community Bangalore here. Yeah. So with that, I just want to take a quick few minutes to have you understand how does the containers, SDN, and all these things connect together. So as we understood right now, with the SDN, we have, I think, typically two parts there. One is, of course, you're doing all the flow, that how the packets are, how the packets need to be, how the packets can be programmed to travel or transfer to a different destination, right? We can put intelligence there. And also we can kind of virtualize these devices, like our switches, network, routers, and all that stuff, right? We can virtualize them, and then we can use them on top of the hardware. So think about, you take a hardware and you deploy a VM on that, and that VM actually mimics a given given switch or given router from a vendor, correct? So if I look at some of the part of it, right? So I assume that you have used a Docker a bit, or you know what is Docker and how does Docker works. So if you know, in Docker we have this Docker zero bridge. So whenever you install Docker, it creates this bridge, Docker zero bridge, and all the containers get attached to it. So initially, when you install Docker, you would just have a Docker zero software bridge, which actually connects to your host interface, and that's it. But as you create container, for every container, it's going to create like a virtual LAN cable, and one endpoint of that LAN cable goes to the container, and other endpoint goes to the bridge. This is one container. Similarly, if I create more containers, you can see that dynamically we can create more such virtual LAN cables and connect our bridge to it, right? So now this is not actually a complete SDN per se, but you can see here we are virtualizing the switch here, correct? And then we can dynamically connect different containers and even send to and fro traffic from the system as well as from the public as well. So basically, we can have our client outside, and then our traffic can come and flow in. So again, this is not, you can think of a complete SDN, but it's a part of it, right? It is doing a part by creating these multiple virtual LAN cables for us, and then of course setting the flow there. Similarly, there is something called as CNI in Kubernetes. So you would have heard about the container network interface or container network interface as a standard, using which we can connect the different pods together, right? So now again, what we do is, once we install base Kubernetes cluster, the networking does not come by default in it. We have to install something called as CNI. And now these CNIs basically are responsible for giving the or attaching the interfaces to our pods we are creating, give them IP address, and set up the connectivity among the different pods what we have on the network. So what you see here is, in the Kubernetes terms, I assume that you know basic Kubernetes understanding you have. So now here we have the API server which requests the kubelet on a given node to create a pod. We say create a pod. Now on a specific node, we are going to have this CNI plugin. This CNI plugin is already been configured. So when you install the respective CNI like Calico, Cilium, Flannel, and all that stuff, so we install that plugin on the given node. Now, when the request come to create a pod, the kubelet would talk to the or kubelet on the node would create the pod and set up the pod network namespace, only the namespace, As you can see, it is not giving you the actual interface, it's just giving you the loopback interface right now. Correct? But now the kubelet, once it creates the pod, sets up the namespace here, it is going to talk to the CNI plugin saying that now give me the interface and assign the IP address to it, right? So now the CNI, whatever you may have, Calico, Cilium, it's going to connect and give the IP address and attach to the respective pod here. So this is how the CNI works in Kubernetes. And now there are different CNI drivers, as I mentioned earlier, like Calico, Cilium, Flannel, and there are many more. So they have different feature sets. Now these feature sets, like for example, first of all, it just giving you the respective IP address and the attachment of the interface. But then if you kind of go back or kind of add more functionalities into the CNI thing, right? It can even detect your network traffic, or it can even basically do the intelligence routing in and out of the network as well, in and out of the system as well, the cloud cluster as well. So all of these features can get added on top of the CNI plugins what you're going to use. And Cilium, which is adding support of EPBF, which is adding more and more features into it. So what is now happening is this CNI, what we have with Kubernetes, again, is a part of the entire SDN story, right? So SDN is much bigger, but this CNI still plays a part of it. And as we are adding more and more features, or as we kind of giving more power to our CNIs, right? They are kind of taking some of the features from the SDN and they're implementing by themselves as well. So Cilium is one such example, which is kind of uh, adding very interesting features like doing the cluster mashing and all those stuff there. Hope this makes sense. Now, while we are here, talk about the VNF and the CNF part to it. So we discussed again. This is again how does the containers are playing very big role in the entire SDN ecosystem there, right? So traditionally, if I have to kind of deploy the, let's say, think about you are deploying the network, right? A typical 2G, 3G network, and so on, right? So earlier, what used to happen is all of these different things. Again, I don't know the kind of complete details about all of these things, but the idea is that let's say setting up the 3G network, correct? Now, 3G network would, when you set up the 3G network, you would require compute power there. And earlier, what used to happen is there used to be very specialized software which used to build for just handling the telco workload. So I'm just talking about in terms of the telco workload here a bit. So if you are setting up again 2G, 3G network there, right? You would need to set up this proprietary hardware. So, for example, if you are kind of bound by the Nokia or Ericsson, right? You would be only using their hardware and software combination to set it up. Now, by doing that, what happens is, let's say if I am a vendor which I want to provide more feature set, or if I have built something, I cannot do it because it's completely proprietary. And unless and until the vendor gives me, I cannot do that. So from their perspective, we move to the virtual network function. So whatever you see these functions or whatever the soft hardware they had, right, to set up that network, switch, and all that stuff, right? It is now being done in terms of VNF, which is virtual network function, which are powered by VMs. So rather than now implementing them as proprietary hardware, what we are saying is we are going to get VMs and we'll attach to the network. And whatever the feature I need, for example, I just want to tell you that you want to encrypt traffic between the two endpoints, right? So all those things can be now done in terms of the virtual machines. And you can implement all of those features quickly because you can manage VMs much more faster. And these VMs can run on a regular hardware. So you don't require a specialized hardware anymore, but you can run them on a regular hardware. So I can take typical machine of x86 or AMD machine or whatever, and then you can deploy VMs on that. So deploying the workload like telco became very easy with the virtual machines because you can now, uh, what I mentioned earlier, right? Whatever the devices we had earlier, they are now VMs. And once you build a VM, you can take the VM anywhere. Now to the next level is we are coming to the CNF, which is container network functions. So now rather than deploying on VMs, we're deploying on containers. So as you know that containers are more lightweight than VMs, and we can scale up, scale down containers more easily, and it is more cost effective as well. So now what is happening is all of the workload of like 5G and so on, they are implementing using the containers, right? So now whatever the proprietary hardware used to come right earlier, they can now be just containerized. So we have now microservices, and these microservices can mimic the actual hardware. So now in the entire network, you would be just running containers and the pods, you can say, and they can do all of these things for you, like packet transfer, like all of the logic, what we were discussing earlier, right? I want to control the flow between two endpoints. I want to control the bit rate and all those things. So the CNF is the next level of doing these things, and in a much more easier and faster way. So if you know all the 5G network, right, they are kind of being implemented by the CNFs. So all of these features are coming up at the container level. So we are kind of so so SDN is there to kind of control the flow, but all these devices what you require, right, to actually do the data transfer and all those things, they can be containerized. Correct. That is where the things are kind of moving. Thank you, Anjana, for your time.